Hey all, welcome to this session where we'll be understanding eigenvalues and eigenvectors. I'm sure that you know by now how to calculate them. And before everything else, hey all, welcome to let's try to understand them, okay? Okay, this is my profile. I have done my master's from IISc Bangalore. I also have experience of working in a PSU called BHEL. I worked there for around 2.2 years. Okay, so first of all, let's try to understand the concept of linear transformation. Let's say there's a vector I plus j, and this is actually represented like this. Okay, a column matrix. Okay, for example, 2i plus 3j is going to be represented like this. Fine. Now, what you are going to do? We are going to rotate this vector by 90 degrees. So, I am going to write it, rotate vector by 90 degree anti-clockwise. This is what we are trying to do. Okay. Okay. Now, to rotate a vector, we have a transformation matrix. That matrix is given by something like this: cos alpha minus sin alpha, cos alpha. This is actually transformation matrix or rotational matrix. And here transformation is same as rotation. Okay, so we will visualize it. Just hold on. So what we are trying to do is we are trying to rotate this vector anti-clockwise through 90 degrees. So what you are going to do? We put here alpha equals to 90 degree in this matrix first. Okay, and let's call it A. So, A equals to, what do we get? 0, minus 1, 1 and 0. Yes? Yes? Cos 90 0, minus 1, 1 and 0. So, okay, let me now erase it all. Now, if I multiply this matrix, whatever A I have written over there, sorry, 0, minus 1, 1, 0, with this vector 1, 1, what I get is minus 1 and 1. And why we are doing it, it will become clearer to you. Okay? Fine. Fine. So, this is A, this is X, this is, let's say, it's B. All right. So, this was the vector that we started. Now, can you plot this vector in this two-dimensional space? Where would it be? It would come somewhere over here. Right? This will be minus I plus j, that can be represented by minus 1, 1. Yes? Yes? Okay. Now, you can check that this angle is actually 90 degree. All right. So, what we did, we transformed this vector to this new vector by multiplying the old vector with a matrix, a transformation matrix. That's what we did, right? Isn't it? So, whenever we are multiplying a matrix with a vector, and when you are getting a vector, this vector is the result of linear transformation. Yes? Did you get it? Did you get the concept? What does A into X mean? It just means that a vector, initial vector that was there, it is just getting transformed to a new vector, that's all. All right? Yes. Now, why eigenvectors? Now, this discussion is very important. Let's say if you clear GATE and if you go to IISc Bangalore and they ask you what are eigenvectors, and if you say something like this, Ax equals to lambda x, x is the eigenvector, they are not going to consider it. All right. Now, let's try to interpret the meaning of this. Okay. Now, what is A into x? We just now we have discussed A into x is linear transformation. So, the linear transformation should be in the direction of the same vector. This is what it means. All right. For example, there is a vector x. If I multiply this with a matrix and the overall magnitude of the resultant right hand side becomes a scalar multiplication of x, then we say that x is an eigenvector. I'm sure that is getting a bit tougher. So we'll take an example, then try to understand it. All right. And we'll also try to understand that why we are calculating this thing called eigenvector. So let's move ahead. Let's not just get into theory. Let's also try to solve it. Okay. Okay. Fine. Discuss on eigenvalues and eigenvectors for this matrix. Fine. This matrix is given 2 by 2 matrix to you. Okay. So what we have said it, eigenvectors satisfy Ax equals to lambda x. Yes, and these are A is transformation matrix, X is eigenvector, lambda is eigenvalue. All right. Okay. Now let's say this is equation 1. Equation 1 can be written as A minus lambda into x equals to 0. Can it be written like this? Is it correct? Can it be written something like this? Mind you that A is a matrix and lambda is a scalar, right? So, if I say that what is 4 cows minus 2 horses, what is this? Can you answer this? 4 cows minus 2 horses. Can you answer? What is the value of this? What is the value of this? It doesn't have any value, right? So here also this A minus lambda, there's a problem with that because A is matrix, lambda is a scalar, so I need to convert this scalar into matrix. How do I convert a scalar into matrix? Can you tell me? I just put I over here. Now it seems mathematically correct. Yes, now it seems mathematically correct. I hope you understood the concept, why this I is required over here. What is I? I is identity matrix. If A is n cross, not n, if A is 2 cross 2 matrix, then I is something like this, 1 0 0 1, right? If A is 3 cross 3 matrix, then I is something like this, 1 0 0 0 1 0 0 0 1. I hope you understand all this. Yes, this is very basic stuff. So I put I over here. Now I am going to erase all of this. Now, after some time, how do you solve this actually? After some time, you will know that this is a homogeneous system of equations and it will have non-trivial solution. It will come to you after some time, okay? Maybe someone else will take it or I will be taking it. It will have non-trivial solutions only if modulus of A minus lambda I equals to 0. But for that, until that amount of time, you just need to accept this. Okay, it has a reason why we are doing something like this. This is for non-trivial solution. Yes? Okay, fine. Now, let's look at this matrix over here. This matrix, let's say, shows you state of stresses in a plane, all right? So, I am going to write sigma 1 1 equals to 2, sigma 2 2 equals to 2, tau 1 2 equals to tau 2 1 equals to 1. Let's say. Okay, fine. Now, what we are going to do? We are going to put up this matrix in this equation. Okay. Now here, this matrix is of, let's say this is A equals to 2 1 1 2. All right. And what should be lambda for this? Sorry, I for this should be 1 1 0 0. Is it correct? Because A is of 2 cross 2 dimension, I should also be of 2 cross 2. Yes? Okay, fine. Now what we are going to do, we are going to put this in equation number 2. And what we get? Mod of 2 1 1 2 minus lambda times 1 0 0 1 equals to 0. All right. Yes? Okay, fine. So, let's go to the next slide. So, what we are going to do, 2 minus lambda 1 1 2 minus lambda equals to 0, and you can solve this. Can you please solve this and come back? Yes, Shweta says that 3 and 1 is the answer. Obviously, yes. So, if you can quickly do this. So, lambda equals to 1 and 3. Yes. So, just hold on. I just want you to give what exactly and why exactly are we going to do this? All right, just hold up. I know that you can solve them. I know that you can find the answers and all. Let's just do some visualization after some time. Okay, fine. Now, separately we have to put the values of lambda equal to 1 and 3 in this equation. A minus lambda I x equals to 0. This equation was there. I am going to use this again. All right. So, A minus lambda I into x equals to 0 was there, and the original equation, the original matrix was 2 1 1 2, right? And you realize that the sum of two eigenvalues, let's say lambda 1 equals to 1, lambda 2 equals to 3. Yes, if you add lambda 1 and lambda 2, that is 1 plus 3, that is also trace, which is sum of diagonal elements. Yes, that is sum of diagonal elements here, which is 2 plus 2, and lambda 1 into lambda 2, you must be knowing all this, is nothing but 1 into 3, that is determinant of A equals to 4 minus 1 equals to 3. Yes? Yes? Okay, fine. Now what are we going to do? We are going to quickly find eigenvectors, and I suppose you know how to find eigenvectors. What you need to do is use this equation and substitute each values of lambda 1 and lambda 3 there separately. Okay? Yeah, exactly. I'll tell you exactly. Real life situation I'm trying to get into there. I'll tell you where exactly is the application of eigenvalues and eigenvectors. All right? Fine. So, can you quickly find eigenvectors for me? I suppose you know all this. If you don't know all this, we are going to use this equation, okay, and put lambda 1 equal to 1 firstly and lambda 2 equal to 3 second times. Okay, fine. This thing. Okay, then I am using this. I am going to write, firstly I am going to write lambda 1 equal to 1, okay, here. So, what we have 2 minus 1, 1, 1, 2 minus 1, okay, into x, let us say x is x1 and x2 equals to 0. I just put lambda equal to 1 in this equation, that is all. A is this and I, you know, is the identity matrix. So, can you please solve it? What do we get quickly? We get x1 plus x2 equal to 0 and x1 plus x2 equal to 0. Yes, two equations we have gotten. Sorry. Okay. Now, can you tell me how many solutions will these two equations give? Can you solve them? Quickly, quickly. Two solutions you say, Shrikant, two solutions, he says two solutions are possible with this. How many solutions? See, these are two lines with two variables. For example, if I say y equal to x plus 1 and y equal to x plus 1 are two lines, how many solutions do they have? Infinite. Yes, obviously, because these are same lines and they overlap. Yes, so here also they will have actually infinite solutions. Good, good, Akash, good. Okay, fine. Now, how do you calculate the infinite solutions? From this, we write x1 equals to minus x2. Wherever this is getting satisfied, we have one eigenvector. All right. So, one minus 1, can it be an eigenvector? I just put x1 equals to 1, so x2's value comes out to be minus 1. Can it happen? Is it possible? Yes, yes? Yes, yes is the answer. Obviously, it's possible. But what about this? Minus 1, 1. Is it a possibility? Yes or no? Just look at this equation and try to tell me. Is it a yes or a no? Obviously, it's yes, because once I put x1 equal to minus 1, x2 becomes 1. Is this a possibility, 2 minus 2? Is this a possibility, minus 100, 100? Yes, all of them are possibilities based on this x1 equals to minus x2, because we have infinite number of solutions for equation 1 and equation 2. So, what did you understand? How many eigenvectors are possible here? It's very important, guys. It's very, very, very important. This is the crux of it. You need to understand this. How many eigenvectors are possible? How many? Infinite. Infinite eigenvectors are possible. Okay, and you will see that these are eigenvectors, they fall in this line. Let's say this is x1, let's say this is x2. So, any vector falling in this line is an eigenvector. Yes? All right. So, similarly, can you find the next eigenvector corresponding to lambda equals to what we did? We did it for lambda equals to 1 or 3. 2, 1, 1, 2. This is the thing. 2 minus 1. So we did it for lambda equals to 1. Can you do it for lambda equals to 3? Because this was the equation 2 minus lambda 1, 1, 2 minus lambda. So lambda equals to 3. Yeah. For lambda equals to 3, what will you have? You will have eigenvectors like this 1, 1, 2, 2. You can find it out, okay? Whenever you go to your home, you will find it out. You will have eigenvectors like this 3, 3. How many numbers? Infinitely many numbers, okay? And you will see that all those who are falling in this line, this is x1 equals to minus x2. This is x1 equals to x2. This is for lambda equals to 3. Yes? Yes? Can you tell me, if you take one eigenvector, any eigenvector along this, let's say you take this eigenvector for corresponding to lambda equal to 3 and you take this eigenvector for lambda equal to 1, what is the angle between the two? What is the angle between the two? Can you find it out? 90 degree? Yes, it is 90 degree because this is x1 equals to x2. Alright, its slope is 45 degrees. Similarly, this is actually x1 equals to minus x2. If you are not understanding them in terms of x1, x2, this is nothing but y equal to x line, this one. And this is nothing but y equal to minus x line. Okay. So this is 45 because the slope is 45 degrees and this is also 45. Alright, so this becomes 90 degree. Is that okay? Good, good. It's great to see that you are all following. So what it means? See, this was the matrix that we started with and it's a symmetric matrix, right? Agreed? A is a symmetric matrix, right? Yes? What's a symmetric matrix? So I am going to write over here, A is a symmetric matrix. Okay? A equals to A transpose. Yes or no? No, determinant equal to 0 is singular matrix. Alright? Shreyas, determinant equals to 0 is singular matrix. Here, A equal to A transpose. Is it happening? Yes? Yes. Okay, fine. So, and if you take two-dimensional stresses, okay, I am coming to mechanical engineering, a bit of it. If you take two-dimensional stresses, I am going to firstly erase them. Okay, sigma 1 1 equals to 2, sigma 2 2 equals to 2. Again this problem is coming up, tau 1 2 equals to 1 and tau 2 1 equals to 1. This is also 2. These are two normal stresses. Okay. and these are the shear stresses, sigma tau 1 2 equals to tau 2 1 equals to 1. This you will understand. Okay, this will come up in strength of material, but let's say these are the states of stresses that is given to us. Then let's write a matrix by like this: sigma 1 1, tau 1 2, tau 2 1, tau 2 1, sigma 2 2. This is stress tensor. This hopefully you will read in strength of material, but yes, let's talk about this. Let's talk about real life examples. Okay, and let's take similar values from this matrix A. So what we have: 2 1 1 2. Okay, fine. No, these are just normal stresses. Okay, normal stresses are this. Shear stresses can be normal shear stresses. All right. Okay, and we are just talking about two-dimensional stress system over here. Then what does then we calculated the eigenvalues of this, and it turned out to be lambda 1 equals to 1, lambda 2 equals to 3, right, if I am not wrong. So if you see, these are the principal stresses. This is a very shortcut way of finding principal stresses. You can check it using that formula, whatever you use in strength of material, and using this. All right? Yes? Okay? So I'm going to repeat it. That if a stress tensor is given to you something like this, and information is given to you something like this, you form a stress matrix and you find eigenvalues of stress matrix, you are going to get principal stresses. Now it's amazing, you know, there are so many examples, so many applications of eigenvalues, but for you guys this is the most prominent one. Okay, so if strength of material, if you get such a question, please straight away go and find the principal stresses. Okay, it's all my welcome there, Shreyas. Fine. Now talking about eigenvectors. Eigenvectors, we said that are along this line and are along this line. Yes? So the first eigenvector is giving the first principal plane. All right, and you can correlate which one is a major one and which one is a minor one, because this is for lambda equals to 3 and this is for lambda equals to 1. All right. Yes, I am going to repeat it. These eigenvectors, all of them which are along this line y equal to x or x1 equals to x2 in this case, are principal planes. Principal plane number 1. On the second eigenvectors along this line are principal plane number 2. All right. So major principal plane is corresponding to this, minor principal plane is corresponding to this. Is that good? Say yes if you understood it. Is that good? Is that good? So this is the biggest, application of eigenvectors for mechanical engineers, and it's amazing. Now what we have done is we have found out new coordinate systems here. Let me erase them all. Now what we found out is, what I have done is I have just transferred these eigenvectors here. Okay, I have just transferred these eigenvectors. Those are mutually perpendicular, and as you know that principal planes are also mutually perpendicular. Right? Yes? Okay, fine. So I transferred it here. Now what we have new coordinate system which is more computationally efficient. Okay, so that's why we are calculating eigenvectors, and that's why we are calculating eigenvalues, so that we need new coordinate systems which are more efficient, computationally more efficient. What it means is that if you calculate a linear transformation over there and you calculate linear transformation over here, this is going to be faster. So please understand that if you ever go to IISc Bangalore or great institutes, remember all these concepts, and yes, ask questions. That why are we doing something like that? Obviously, you can calculate eigenvalues. Anyone can calculate eigenvalues, right? But where are they applied and why are they important? This is what we are talking about here. And this is what you need to find out always. Don't accept anything like that. This is the level of understanding that we need to clear ESE and GATE. Alright? Alright, so I think I gave you a very insightful topic, and I hope that you learned from it. And I'll be back tomorrow. With the continuation of the discussion that we have done. We'll also take a few questions, few more insights about the matrices. Stay blessed and be happy. Okay, thank you very much. Okay, Shreyas has one question. This is a very lengthy process. In ESE, there are only few minutes to think and to mark. So what should be done? Yeah, Shreyas, tomorrow I'll come up with few tricks and tips. All right, that can be done in ESE as well as in GATE. Obviously, this is a very lengthy process, but I had to do it. So that you understand why we do it. Yes? So tomorrow I'll be coming up again, and let's see where we take it. Okay? Sure, Shreyas. Thank you very much. I also enjoyed your company. Thank you very much for tuning in here. Be blessed by the divine, and be happy, be blissful. Okay, my name is Rahul Kanyal, dear Arun Kumar. Okay, I'll be back tomorrow. Thank you very much.